this celebration. So Zoe Wyatt got her undergraduate degree in Cambridge, and she moved to Edinburgh to do her PhD, and now she's back at Cambridge, where she is an assistant professor, and she is very interested in general relativity. In particular, she likes to analyze partial differential equations which arise in string theory, in gravitation, in cosmology, and in particle physics. And today we are going to learn about the new phase transition in cosmological fluid.
Let me mention that we are very proud that Zoe was part of her PhD spent in Vienna, working with that. We're very proud of having had you in my group.
Thank you, absolutely. So clearly I'm having trouble with my, don't have a hairline today, sorry. All right, thank you so much for having me here. It's a real honor. I thought I'd tell you the first time I met Piotr, I was a PhD student. This was about 7 years ago. And I met him at a conference, the Central European Relativity Seminar, which I think is a fantastic initiative that Piotr has kind of supported, where he brings together lots of junior mathematicians to present their research, so PhD students in particular. So I met Piotr, and it was my first time meeting him, and I was really stressed because I didn't know how to say his last name. I didn't know how to pronounce it. I'm from Australia, and we have beautiful surnames. We don't have as many of them over there.
Nobody knows.
But, right, well, that's it. And so I remember I went up to you. I distinctly remember in the hall. And I think most people, when they meet someone like you, they obviously say, hello, Professor Chruściel. And I was just so nervous at the thought of saying Chruściel. I was like, hi, Piotr. And I remember you were slightly taken aback at the fact that I was saying your first name straight away, but it was only because I was a bit nervous about your surname. Good.
I was very glad.
That's it. Okay, so today I'm going to tell you about some recent work that I've done, in particular with collaboration here with people in Vienna. Okay, so I am also interested in the Einstein equations of general relativity, and I'm in particular interested in cosmological solutions. So what was quite good is we just had the talk by Hans. So Hans was looking backwards in time. He was going towards the singularity, and now I'm going to go forwards in time. So at least we've put the talks in the right order, which is great. And I guess the big picture goal is to understand the dynamics of matter in our early universe. I'm not claiming that we have solved that yet. Okay, there's certainly a lot of things to do, but I hope that this is maybe one step that is fruitful and telling us something interesting. And so I've got here one of these nice pictures that you can get of our cosmological of the model that we have for our universe, okay? And so we sit here and we're detecting light that has been emitted from billions of light years ago and things like this. And so I guess I can just tell you in a nutshell, we have very good mathematics that describes kind of the more recent epoch of our universe, which is when we have dark energy accelerated expansion. But what I'm interested in is kind of earlier epochs in our universe and trying to understand some of the matter dynamics there. But I'll be working in a very idealized math setting, so lots more to do. And everything that I say today is joint in some subset or all of with David Feynman, Maciej Miliborski, and Max Offner, all in Vienna, and also Todd Olenek in Monash in Australia. And so I should just say also thanks a lot, because when I was a PhD student, I was in Vienna for 6 months, and I had a really wonderful time. So I very much enjoyed being here in the gravity group. Okay, so the starting point in these future dynamics is to make some simplifying assumptions. As we've seen in Hans's talk, the Einstein equations of general relativity are incredibly complicated. They're nonlinear partial differential equations. And so it's okay to make some assumptions to get you going. This is something that cosmologists do in their field very, very readily. And so the starting point to have is that at very, very large cosmological scales, we see the same distribution of matter regardless of the direction that we look in. Okay, and so this is what we call isotropy. And so this is based on observations of the cosmic microwave background. okay, which is a kind of thermal black body radiation that was detected in the 60s or the 70s. And it is a relic from our early universe. And what is quite amazing is that it is so uniform. Okay, so when we detect it looking that way out from planet Earth versus the other way, we're seeing a uniformity to, I guess, 1 part in 100,000. So something that is incredibly uniform. Now, we also suppose that our position here on planet Earth is not special. Okay, so the fact that we see isotropy around Earth, we suppose that that will be the same as if you're on the other side of the Milky Way or something like that. Okay, so under the assumption of isotropy and homogeneity, spatial isotropy, spatial homogeneity, we can reduce the degrees of freedom in the Einstein equation significantly. And in some sense, you can get your foot in the door and you can start to study some things. Okay, so this is broadly, these assumptions are what I'm calling the cosmological principle. And so this forces our space-time metric to take a very specific form. So we have a time interval, let's say, and a 3-manifold M, and our metric G is very constrained. Okay, so in particular, we pick up a split structure here. We have a function A of Tc. So Tc here is just is a time coordinate that I call cosmic time, because that's often what's done in parts of cosmology. The factor out the front is called the scale factor. So this is measuring the volume growth of our spatial slices. And we know that our space-time is expanding. Okay, it's one thing we do know is that our universe is expanding. And so in particular, the first derivative of this scale factor will be everywhere positive. Now, something else that we have is that, again, this isotropy, the symmetry assumptions that we have in this system really limit the possible geometries that you can have for the 3-manifold. So M and G here, this is a Riemannian manifold. The overall spacetime is a Lorentzian manifold, as you see here with the minus sign. Okay, and so in particular, this 3-manifold is restricted to have constant sectional curvature. And so roughly speaking, the possibilities that I can have are some hyperbolic space or a quotient of a hyperbolic space, R3, and in particular, what I will be looking at today is the quotient of R3, I'll take T3, or the sphere, okay, or S3. So this is the geometry setup, and in the Einstein equations, if you recall them back here, okay, I have on the left-hand side, I have geometric aspect, I have geometric quantities, the Ricci curvature tensor, the Ricci scalar, a possible cosmological constant, and on the right-hand side, I have some matter fields. So again, the isotropy and the homogeneity really restrict what these can be. And in particular, all of these symmetry restrictions force these matter fields to take the form of what we call a perfect fluid or an idealized fluid. Okay, so we end up on the right-hand side, the matter takes the form of a fluid with energy density rho, some pressure P. The fluid particles are moving with 4 velocity u. Okay, and you can normalize this because they're time-like. We have the local conservation of energy momentum in general relativity, and that imposes then 2 equations of motion. So the first of these, I guess, is from the 0 component, the other one's from the ith component. Okay, and so these 2 equations constitute what we call the relativistic Euler equations. And perhaps the way I've introduced them, you might think, oh gosh, they seem very artificial how I've got them, but they do actually naturally generalize the non-relativistic Euler equations in an appropriate setting, okay, in particular for a perfect compressible fluid. Okay, so it's kind of introducing a fluid dynamics model that is covariant under Lorentz transformations. Okay, so this is the geometry, this is the matter that I'm interested in, and let's think about the dynamics. Okay, what are the PDEs telling us? Well, again, under all this symmetry, instead of having a whole bunch of variables that had lots of different degrees of freedom, we now reduce the number of unknowns. They're just merely the Einstein-Euler equations in particular, reduced to some fairly simple ODEs to write out. So the first of these you can view as a continuity equation, okay, as you normally would get in fluid dynamics. And we also have another equation called the Ricci-Duri equation. So I guess the thing that I just want you to see here is that we have some very concrete, simple ODEs that you can study. The dynamics here is clearly going to be affected by the energy density, the pressure, that should be the same P, cosmological constant, lambda, also possibly kappa, or sectional curvature. Okay, so this is a system of equations. You can study these also using dynamical systems methods and things like that. I'm just going to tell you some special solutions to these equations, which are going to be relevant to what I'm interested in. But before I do that, I'm going to close my system because that's how we solve equations. Okay, so I have an equation here for rho, and I have an equation here for the scale factor. It turns out, I think one of these is basically the integral of the other. So I need another equation to close my system. And so in the cosmological setting, this is most often done using what we call a linear barotropic equation of state. So here I take the pressure, it's barotropic, so it's just a function of the energy density, and it's linear, so it's equal to K times the energy density rho. This is obviously a simplification. I mean, in the standard model that cosmologists use, my understanding is this is really what they use. Okay, it is very simple though, and maybe in future we can try and look at more general equations of state and see what we get. But at least to start with, this is what we consider. So we're working in units where the speed of light is normalized to 1. So that's why this number k here is less than or equal to 1. And you often see this number k here written as the square of the speed of sound. Okay, so it's measuring the speed that the fluid sound waves are traveling at. So it can't travel faster than the speed of light, so that's why k is always less than or equal to 1. Actually, in cosmology, what is kind of more interesting, two really interesting parameter ranges that people study are the following here written in red. So k equals 0 is when you have vanishing pressure. So this idea, I say here this galactic epoch because your fluid particles are galaxies, okay? And they're so far apart that they don't interact, okay? So they're pressureless. But cosmologists are also interested in this other case here too, which is where k is equal to 1/3, and this is what they call radiation. And so here we're thinking of kind of highly energetic particles, which are let's say some gas of photons or something like this. And we might, instead of using electromagnetism, we might be modeling them as a fluid. Okay, so in our early universe, cosmologists believed that the matter could be taken to be, the matter components were really, very early on were dominated by radiation fluid. And as our universe expanded, as it cooled, matter started to clump together, started to disperse apart, and then eventually we reach an epoch where we can take k equals 0 as the dominant matter model. Okay, so in the kind of the world of cosmology, there's a transition between these two, which I guess we're trying to look at from the maths point of view. Okay, so maybe just one concrete thing that we can do straight away. So if I take this linear barotropic equation of state and I just substitute it into the continuity equation, I get here a differential equation that I can just integrate up. And so I see that in fact, the energy density times the scale factor is equal to a constant. Okay, so for example, we know that the scale factor is growing, so we see that the energy density rho is diluting, but it dilutes at a rate that depends on the kind of fluid that you have. Okay, so already we see that there's going to be different results depending on this fluid parameter k. Am I talking too fast? Any questions? We're good. I've not given a talk actually in a while, so who knows what could happen. All right, so let me tell you now some special solutions. I'm going to tell you 3 special solutions that are kind of widely studied and very much relevant to what I'm interested in. So the first class of solutions are called by lots of different names, but I think most commonly they're called the Friedmann-Lemaitre universe. It's a matter-dominated solution. And so it's matter-dominated, so I take the cosmological constant to be equal to 0. This is, the metric that I had before. I've now I have a specific function for that scale factor, a of t. And you'll note that it has some rate that depends on the fluid parameter k. It's called the flat solution because I'm just taking the flat metric here on the torus or on R3, and I've got my energy density, which is decreasing at some rate proportional to 1 over t squared, and rho 0 is just a constant. So this is, I think, one of the fundamental models used in cosmology, particularly the standard model of cosmology. And it has these 2 important cases that I was saying before. the case where the cosmologists used to model the radiation epoch in our universe, and then the later epoch of dust. And so you see that there's a change in the scale factor. Okay, so when we're in the case of radiation, very early universe, the scale factor grows like the square root of t, whereas if we're at the later dust epoch, it grows like t to the 2/3. And both of these examples, all of these examples actually for the Friedmann and Lemaitre universe are examples of decelerating expansion. So everything a dot is always bigger than 0, but in particular here it's decelerating because the second derivative is negative. That's going to be quite important. So another important special solution to the system of differential ODEs that I had up before is the de Sitter universe. So this is what we use to, this is what we believe our universe is currently kind of asymptoting towards. And one way to, let's say, model the accelerated expansion that we, that we observe in our universe is to allow the cosmological constant to be bigger than 0. So the key, I guess the key thing to observe in this solution is that I have a scale factor here, which is an exponential function of the cosmic time. And so in particular here, the second derivative of A is strictly positive. So this is an accelerated model of our universe. So I have something that's accelerated, I have something that's decelerated. Is there something in the middle? Yes, there is. And this is called the Milne vacuum universe. So this is I guess kind of, sort of different choice of the sectional curvature here, but the key observation to take here is that my scale factor is a linear function of t, so in particular the second derivative vanishes. Okay, so we have these three solutions. There's lots of solutions. In general, there's lots of solutions to the Einstein equations. Because they're so nonlinear, we have to have a lot of symmetry assumptions in them. And it can be hard to, I guess, know which one you should pick. Okay, which one should you pick for your model of our universe? And so we know different things about these models. So for example, a decelerating universe, we know that that will eventually go towards a big crunch. We've got kind of this one where it's, this one is coasting along. This is the linear expansion. But cosmologists believe that our universe has kind of transitioned between different models. So it started at something that was decelerating, and then more recently, we're now in this epoch where some kind of dark energy has taken over, and so now we're in an accelerated epoch. So what would I like to do from the point of view of mathematics? Each of these different solutions, they're highly symmetric, and you might ask, how generic are they? How stable are they to small perturbations? So we can study the stability properties of these solutions as an initial value problem. Now, it's always important to remember that for general relativity, this is quite a subtle question because there's no canonical choice of time and space in general relativity. So what on earth can it mean to have an initial value problem when you don't even know what time is? Okay, so it is a subtle question to put this on kind of good mathematical grounds. This was the paper that Hans mentioned by Schocke, Bruchar, and Gerock. And so let's say, I don't really want to get into too much of what is that choice of time and space. So I've just ambiguously left them as these red arrows, some flow of time. But the intuition to have with these kinds of questions is the following. So if I were to take some t equals constant time slice of one of these special solutions, that would induce some geometric data on that hypersurface in the form of a Riemannian metric and a second fundamental form, exactly as Hans was telling us about. And now you might say, okay, well, what happens if I add a small perturbation to that initial data? Okay, what if I add some small epsilon bump? How does that small perturbation evolve under the Einstein flow? Now, the equations are nonlinear. Gravity is attractive. Okay, so you could very much imagine that actually some kinds of perturbations could interact in a way that would lead to a shock, whatever that might be, some breakdown in your solution, some finite time existence to your PDE. Okay, so it very much could be the case that, and we know that we form black holes, right? So we know that some bad things could happen. But it also could be that you asymptote, your small energy perturbation just radiates away, and actually you end up at the original space-time that you started with. You can also have, so I guess this middle arrow here is the view of asymptotic stability. You can also have a kind of orbital stability. So in particular, if you perturb a black hole, you're not going to expect to go back to the same black hole. Okay, so in there you could have a kind of orbital identity, orbital result. So these are the things, this kind of question is what I'm interested in for the Einstein-Euler equations. I have done some work on, or we have done some work on Einstein-Euler, which I'll mention later on, but actually kind of the more recent things, we've made the big simplification that we're actually just fixing the geometry. Okay, so we're going to fix the geometry to be some Lorentzian metric and actually just study the relativistic Euler equations and see what we get from that. And from there, you could then look to add in the Einstein equations. But certainly the full dynamics are a lot harder. Okay, so what have people done? What do we know? So now let's say I'm really thinking about the relativistic Euler equations. I've kind of fixed gravity for the moment, and I'll come back to that in a moment. So if we just think about the relativistic Euler equations, then we've known for a very long time that the non-relativistic Euler equations develop shocks in finite time, even from smooth data. Okay, so we get a shock or a singularity in the sense that the fluid variables themselves will remain bounded, but some derivatives will not. They'll diverge. So this is a result that holds for the non-relativistic, so the standard Euler equations that you might know. And it was shown by Chruściel that this naturally extends to the relativistic Euler equations. Okay, so in particular, Chruściel showed that small solutions of the relativistic Euler equations develop singularities in finite time. He also did this on a fixed geometry, okay, on a fixed Minkowski geometry. So Euler equations seem quite bad. It seems that we're going to develop shocks. And then now comes the idea in the cosmological context, which is that if you have very fast cosmological expansion, your manifold is, your space-time manifold, which your fluid moves on, is being pulled apart in time. And so you could just literally think that whereas before you might have had kind of two fluid characteristics coming along and intersecting, and this is where we get the discontinuity in the solution, these characteristics could now be pulled apart. Okay, and so you could imagine that actually in the setting of some fast cosmological expansion, we don't get shock formation for the relativistic Euler equations. So this idea was, let's say the kind of first beginnings of this idea come from work of Brouwer, Rendell, and Euler. And so here they didn't look at the whole Einstein equations, they looked at kind of a model problem. But the take-home point is indeed this happens, okay? If the cosmological constant is positive, if we're in this accelerated expansion regime, then small perturbations of the appropriate homogeneous solutions exist globally in time. So we don't have this finite time breakdown. We don't have finite time shock formation. They did also show that indeed if you lose, if you're not in this accelerated regime, actually if you're in a decelerated regime, then you get some kind of, you get your characteristics crossing, and so you would suspect that you've got some breakdown in your solution there. Okay, so this is kind of the first work in that direction, and it's great that I can then cite Hans Ringstrom here, because this, and more generally, this is a result that Hans looked at, which is the Einstein nonlinear scalar field system. And so in this setting, he's taken a scalar field whose potential at 0 roughly mimics the cosmological constant. It has a sign, it's strictly positive. And so indeed here he gets stability for large class of solutions using this accelerated expansion, okay, using the fact that this very, very fast expansion can cause dissipative terms in your PDEs and prevent, basically help you get global existence. Okay, so this is with the help of a cosmological constant. But I guess the key thing to see here is that whenever we allow for a term which behaves like the cosmological constant, then in these cosmological settings, our scale factor, let's say our background B scale factor, will grow exponentially. And so we end up with a second derivative which is positive, and somehow all our PDE dynamics drastically change. Okay, we end up in these highly dissipative settings. And our best observations to date tell us that we are in this, even though we are in this region at the moment, time where our universe is undergoing accelerated expansion, in our early universe, which is when we believe, matter was clumping together and forming galaxies and forming, structures that we see today. In this epoch, we believe that our space-time was expanding at a decelerated rate. And so this is the kind of region that I'd really like to study. And so to do that, I need to set the cosmological constant to 0. Okay, so in order to study this decelerated regime, I guess on this very schematic picture, this early universe regime, we've taken the following approach. So there are kind of quite a few results that I'm just trying to synthesize here. And our idea is to investigate the following. So we study the Euler equations, the relativistic Euler equations, on a fixed Lorentzian geometry. Now, I fix that geometry to just be some time interval times the flat T torus, okay, T3, and I impose a scale factor, which is something called a power law. Okay, as you can see here, it's a power law. It's T to the alpha. This is something that cosmologists do use as well in their models, so it's not something that we've kind of pulled out of thin air. It's certainly something that people study. And so what we're interested to do is understand essentially the phase space of behavior. Okay, so I'm going to have quite a few slides now looking like this, so let me just explain what I'm showing here. So on one axis, I'm thinking about the expansion rate as it increases, and I will have a region where I have decelerated expansion, and I've probably misspelt that, and accelerated expansion. And in the middle, I'm going to have some linear kind of expansion. And I would like to understand, with respect to that expansion rate, the behavior of the corresponding fluid that propagates on this space-time under the relativistic Euler equations. So against this, I'm going to consider the fluid speed, so that's that parameter k. And again, I'm thinking here of the extreme case of dust all the way up to radiation. And you can certainly go forward and you can go further and even down here, but for the purposes of today's talk, I just need to go, just interested in between kind of these two. Okay, so I can make this diagram a bit more specific now. Okay, so I can put in these parameters. So because we're looking at a power law rate of expansion, I've got T to the alpha growth. So here I can put in my parameter alpha. So when alpha is bigger than 1, I'm in the case of A double dot being strictly positive, so it's accelerated expansion. This linear rate here is when alpha is equal to 1, and then the decelerated rate is now when alpha is less than 1. And on my other axis, I've got the fluid speed of sound parameter k, which is ranging between dust, which was k equals 0, and radiation, which is k equals 1/3. So what are we expecting to see on a picture like this? What would you hope to see? You would hope that if your expansion is very large, if your space-time is expanding quite quickly, and you don't have as much pressure, if k is quite small, then you would hope that you would expect not to get shocks. You'd expect your fluid to be somehow stable. Whereas if this expansion parameter is quite small and this pressure is larger, you might imagine that in fact your fluid will develop shocks. Okay, so this is the intuition that you have going in. So we have, yes, okay. So these are some of the results that were known before what we did. So I'm using green for good, which means things are stable, and red for bad, which means that we get instabilities. Okay, so in particular, let's say the community, this was about maybe 10 years ago, was very interested in proving this range here in the parameter space, proving that this is stable. Okay, so picking, some kind of, broadly speaking, picking a parameter where your expansion rate was accelerated, looking at some appropriate homogeneous model, and then proving the stability of that solution. Yeah.
There's no symmetry whatsoever.
Yes.
Assumed on the fluid, right? So
yes.
It's only the background which has a symmetry.
Your fluid is also supposed to be kind of quiet, so it's supposed to be mostly in the time-like direction, and the
pore velocity.
The pore velocity, yeah. So I guess it doesn't have it's like 1, 0, 0, 0 as well. Yes.
No symmetry.
But no symmetry, yes, yeah. Okay, so there's quite a lot going on here, so let me just try to unpack it a bit. So we have, from Chruściel, we have this finite time shock formation result, which we can view as kind of quite useful to view it in the following way. So the Minkowski metric looks like this. And so I could view this as some kind of degenerate space-time where I have just a scale factor is identically 1. Okay, so this is kind of like e to the 0. Okay, so that's why on the left-hand line here, when alpha is equal to 0, I have this red line, which is the work of Chruściel. So this is rigorously showing that the solutions here will develop shocks in finite time. We also have the following red line at the top, which is by spec. And so this also confirms this intuition that when k is large, and kind of, alpha just ends up being, it changes over at the linear point, we do get shock formation. Okay, so again, this is a rigorous result showing that you do get finite time shock formation for fluids, for radiation fluids. But there's a whole body of work that looked at this stable regime, again proving, and now here it really is proving stability for the full Einstein-Euler equations without symmetry. And yeah, so here I've got kind of a few different references to this fact. We've got Helmut Friedrich in the audience, so he's also looked at this in the case of dust and a few other models, I think, as well. And so broadly speaking, that if you are in this accelerated regime, things are good. Okay, and if you're in the kind of exceptional case of dust, where your intuition is that k is small, okay, we wouldn't be expecting to get shocks, we can actually prove stability all the way down to a half. Okay, so in fact down to this regime, it's equal to a half. Okay, so what do we do, which is kind of hopefully adding to this, is we now fill in the picture in the following way. So you'll notice that we're now kind of here, we really didn't know what was happening in this region. We didn't know what was happening on the linear line, okay, when alpha is just equal to 1. And so this is what we've now been able to address in various maybe symmetry kind of things that we're working towards, but let me just explain a bit of this. So we were able to show stability along this line at alpha is equal to 1. Okay, so this tells us that these linear models are stable. But more recently, and we're also, in this case, also able to study the Einstein-Euler equation. So you can also couple in gravity in that setting. But the more recent, I think, very exciting work is this third one here, which came out on Archive earlier this year, because we really look at this decelerated regime and we identify a new, what I call phase transition. So actually, maybe it's better just to stay on this line for a moment. So we identify this line here, which I've denoted in black, which we have a specific formula for, okay? And we can show analytically that for parameters, fluid parameters alpha and k on this side of the line, we get stability. Okay, so this is the first case of stability in decelerated models. Complementary to this, and so our proof, very much relies on our parameters being above this, or to the right of this line, to the right of this transition line. To the left of this, we get numerical results, very much by Maciej, showing that we get unstable solutions here. Okay, so we solve numerically the relativistic Euler equations on these fixed power law spacetimes. We're working under a symmetry assumption, T2 symmetry, but in these regimes, our fluid is breaking down in finite time. The equation only exists numerically up to a certain point. And so I think it's very satisfying that the numerics that we're getting in this regime are exactly agreeing with the complement of the region which we can prove analytically. Now, I mentioned that in this preprint, we talk about the proof of this, this stability regime in T2 symmetry, but we're also able to extend this in upcoming work outside of that symmetry class. Okay, so some of this picture, I mean, I accept is in symmetry, some of it is numerical, but I think it's quite interesting that this is quite a new phase transition that we uncover in this decelerated regime. And this is then just a bit more to comment on it. So where this transition happens is along this following line here. Okay, so K is a function, the fluid parameter is a function of alpha, the expansion rate looks like 1 minus 2 over 3 alpha. I think one thing that is quite interesting is that you'll notice here that we've got a kind of a bit of a green line here, and then we jump straight into a red region above here. Okay, so what we're getting is a dichotomy between the behavior of the fluid as K tends to 0 and is exactly equal to 0. So in the exactly, let's say, pressureless model, things look quite stable. But if you just add a tiny bit of pressure into your model, if K is just slightly bigger than 0, our numerics would indicate that this is unstable. Okay, so there's a nice dichotomy here, and I think it's quite interesting because this region is exactly the region where the genes instability is supposed to arise. This region is also where cosmologists typically use dust as a model for lots of things that they do, but it could be that, you know, maybe using exactly pressureless fluid is perhaps an oversimplification. And if you just add a little bit of pressure in here, your dynamics could change quite a bit. So I think it's quite interesting to better understand this. And what I've also put on this graph here is the first special solution that I had on a previous slide. So this was the Friedmann-Lemaitre solution. And so you notice now that, so this is this brown line, and so this fully lies in the unstable regime. Okay, so it's I think a very interesting question now to consider what would happen if you couple gravity into this, what would happen if you change your equation of state. Kind of, there's a lot of questions that I hope we can look to explore. So I've only got a few minutes left, so didn't quite know the audience, so I've just put one slide where there's a bit of PDE. But I do think this is quite nice. So broadly speaking, you know, kind of big picture PDEs, we have two mechanisms at play here. We have a decay mechanism, which is coming from the expansion of our space-time. So the decay mechanism, let's say in the PDE language, looks roughly like dt of some function is minus a positive constant over t times phi, that function. So you get kind of terms of this type that appear in your equation. What is the canonical mechanism for shock formation? If you think of the nonlinear transport equation, it looks like this. dt of psi, let's say, plus psi d psi dx psi is equal to 0. So when we're in this decelerated regime, we're looking in symmetry, what we get in our PDEs are exactly like a coupling and a competition between these dynamics. Okay, so you'll see that, for example, this first term here in the V equation, this is like a decaying term. But then you'll notice here on the right, I get this kind of advection, this nonlinear transport term, V dx V. But multiplying this term is a t to the minus alpha, so that's a decaying term. So you get a kind of interaction in your PDEs between all these different, these PDE mechanisms. So in order to prove a stability result, okay, small data global existence result for this system, we need to introduce a corrected energy to the kind of the standard L2 energy that you would have for PDEs of this type. And this induces decay, but only provided we constrain K and alpha in the way that matches up with that phase transition. Okay, so it kind of naturally pops out of this analytic argument that there is some restriction here on K and alpha for these energy estimates to close. And as I've said once before, it's very nice that the numerics in the unstable region are green, at least in the sense that the complement of them is what we can show analytically as being stable. But it would certainly be, it would be very nice to better understand the process of shock formation, which people in the field have very much looked at on Minkowski. It'd be very nice to now understand this in a decelerated, in a cosmological setting as well. Okay, so I just have 2 more slides. So one thing I find quite nice about considering the fluid is that a fluid behaves very differently to a scalar field. And so there's been some work by groups in Portugal in particular looking at solutions to the linear wave equation on power law geometries of this type. And again, looking in the decelerated regime. And one thing I like about the decay results that they get is you get this kind of so they get these, let's say, different L infinity decay estimates for solutions to the wave equation. So your intuition is always that when you're on Minkowski, we have Huygens principle, we have conserved energies, so we must have some kind of decay for our amplitude. Now that decay goes like 1/t in 3 space-time dimensions. But you would imagine that as your space-time starts to expand, well, that decay should get better and better. And so it does, but actually at some point, when your cosmological expansion is a bit too fast, those regions are moving a bit too fast away for your field to disperse into it. Okay, so it's not quite as naive as just thinking, oh, it expands faster, it must decay faster. Okay, there's some kind of, I guess, some interactions happening here, which would be really nice to understand. So in particular here, when alpha is between 2/3 and 1, you're actually getting worse decay than in Minkowski. Okay, so your full effective dispersion is being thwarted by the fact that everything is moving too fast away for your field to get into. What's nice with the fluid compared to the scalar field is that a fluid moves slower. Okay, it has this parameter k, which I've considered between 0 and 1/3, so that's quite far away from 1. And so in some sense, I think we're getting this non-trivial phase transition and things like that because the fluid is sitting on this expanding geometry for longer. It's not moving as quickly as the scalar field, and so it's somehow feeling the different effects of this expansion. And so this is, I guess what I'm saying is that what we get is quite different, I think, if you were to consider other matter models like the massless Vaslov equation. Okay, so this is, I guess, all I wanted to say to you. So this is the summary is that we find these new stable and unstable regimes for perfect fluids in decelerated cosmologies. There's certainly a lot more things that I would like to understand, things like looking without symmetry, seeing if we can turn on some parts of the Einstein equations and analytically understand these unstable regimes. And with that, thank you and very much congratulations to Piotr.